Now another set of terms. The first one is empty set, or we call it null set. It is a set that has nothing in it, so therefore you do not see anything in it, right? So it has nothing. And sometimes we just denote it like this 0 and a slash. So that means the null sets are empty. For instance, this is a null set, like x is a real number where x squared plus 1 is equal to 0. So there's no way you can find x, so that x squared, which will never be negative, plus a positive number will be 0. This is no way, as long as x is a real number. I do know that x could be complex, but we are talking about there's no such real number. So therefore, this is actually a null set. And you can never find a value that is greater than 2 and at the same time less than 3. Okay? Integer. There's no such integer. There are many values that's in between 2 and 3, but there's no integer that's in between, exactly in between 2 and 3, excluding both endpoints. So this is another example of empty sets. Now disjoints, that means the name says they're not overlapping. Is that right? So in other words, they don't have nothing in common. So A intersects B is empty. And we say A1, A2, A3, and so on and so forth, they're mutually disjoint, or we call it pairwise disjoint, if and only if any pair, they have nothing in common. So for when I is not equal to j, then they have nothing in common. Now we say a sequence of sets is a partition of a set A. So here, if this A is equal to the union of all these sets, and also all these sets are mutually disjoint, they're pairwise disjoint. So that's that's this graph kind of depicts what a partition of set A is. For instance, suppose we have a set A which contains 6 numbers, 1, 2, 3, 4, 5, 6. And if A1 is just, set A1 has elements 1, A2 has 2, 3, 4, 5, and A3 has 6. When you combine, they're pairwise disjoint. If you A1 and A2, they have nothing in common. A2 and A3, nothing in common. A1 and A3, nothing in common. And when you union all these, you get A back. So this is a partition of set A. Of course, this is another partition if you want. 1, 2. So set A1 contains 1, 2. Set A2 contains, say, 3, 5. And set A3 contains 4, 6. Now this is also another partition of this set A. The next term is the power set, written as P of A. It is the set, sorry, a typo. It is the subset of, it is set of all, I'm sorry, it is the set of all subsets of A, okay? It is the subset of all sets A. So it's the subset. So it's a collection of all the subsets of set A. Sorry about the typo. Now, for instance, the power set, let's find the power set of this guy, So first of all, we need to find all, that means we need to find all subsets of this guy. So the first one will be actually the empty set, because empty set is actually any, is a subset of any set, okay? And the next one can be, this is a subset of this guy, and this is a subset of this guy, and also this is a subset of itself, right? So therefore, this is the power set of this guy. Of course, to be rigorous, I should use the sets notation. This is the power set of this guy. And similarly, the power set of the sets ABC, you can begin with empty, and then A, B, C, and then sets of 2, AB, AC, and BC, and sets of size 3, which is itself, and then that's all the subsets of this guy, which is the power set of this guy. All right. Now let's take a look at this example. A0 is a collection of integers where the integer can be written as 3k for some integer k. So basically multiple of 3. This basically is the multiple of 3. Okay. And now this is A1 is all the integers so that it can be written as 3k plus 1. So which means multiple of 3 plus 1, which means all the numbers, all the integers, if you divide by 3, it has the remainder 1. So that means all integers with remainder 1. Okay, you can list a few elements from this set, and you see this is actually the fact. And A2 is n in Z, where n is 3k plus 2. So this is a multiple of 3 and a plus 2. Basically, this is all integers with remainder 2. Okay. And the question is this a partition of Z? Is the set of these 3 sets is the partition of Z and all the integers? Yes, definitely, because A0 contains all integers. Because it's multiple of 3, that means the remainder is 0 when you divide by 3, right? So all integers with remainder 0 when divided by 3. And A1, we just explained that it's actually all integers with remainder 1 when it is divided by 3. And A2 is all the integers with remainder 2 when divided by 3. So you see that any integer when it's divided by 3, you can only get one of those 3 possibilities. So therefore all the integers, they will be in one of those 3 sets, right? And plus A0, A1, A2 are mutually disjoint, and every integer is in one of those 3 sets. So yes, it is a partition of the integers. Okay. All right, now let's close this section by doing one more problem. This example shows you how to actually there's a combination of, one is the Cartesian product, and the other one is the union, the set operation here. So it's kind of good exercise. So now let's begin with B union C. Okay, B union C means we put them together, the union of both. So A, B for B, B, C for C. The union of B and C will be A, B, C, right? So the common, all the elements will be A, B, C. So therefore here the A is actually X and Y. I'm going to just list it right below it. B union C is A, B, C, all the elements in B and C. So now this Cartesian product results a order pair, so it will be collection of all the order pairs. And the first a first component has to be coming from A, and the second component coming from B. So we are going to try all the combinations. YA, YB, and YC. I think those are all the possible combinations. So that's the set represented by this one. And similarly, this B and C, that means this will be the elements in both B and in both C. So we see that that's only B is in both sets B and set C. So cross A, which is a set contains two elements. So therefore, this will be all the order pairs. The first component is from this intersection, only one, right? Only this possibility. And the second one is coming from A, so BX, BY. All right, that's it.